everyone, I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. We are doing a series of lectures on the topic waves in one dimensions and harmonic oscillations. We have already covered simple harmonic oscillators and damped harmonic oscillators. And today we are going to discuss about forced harmonic oscillators. So, the brief outline of how we are going to discuss this topic. First, we'll see what are free and forced oscillations. Then we will derive an expression for a forced mechanical oscillator and then get the steady state equation for a forced mechanical oscillator. Understand the phenomenon of resonance, and then we'll go to electric oscillators and define mechanical impedance and electrical impedance. This is how we are going to discuss this topic today. Now, before we start with forced or harmonic oscillator, it is very important to recollect what is a simple harmonic oscillator and then what is a damped harmonic oscillator. Now, in simple harmonic oscillator, what we have seen is we have a block of mass m which is attached to a spring. One end of the spring is attached to the block of mass m and the other end is attached to a fixed support. So, whenever the block is disturbed from its equilibrium position, if this is the equilibrium position, I displace or I disturb it through a distance x and leave it, and expecting all the conditions of a simple harmonic motion satisfied. Means the surface should be a frictionless surface and there should be a restoring force to bring it back to the equilibrium position. So when we disturb it, this object tries to come back to its equilibrium position. In fact, this object will oscillate or vibrate about the equilibrium position. Now, the force that brings it back to the equilibrium position, we are calling it as restoring force. F is called the restoring force. This restoring force is proportional to the displacement and always acts in a direction opposite to that of the displacement. The force acts in a direction opposite to the displacement, and K is the spring constant. So whatever proportionality sign we remove, we put a constant, and the constant K here is the spring constant, X is the displacement. So what we have here is F is equal to minus Kx. Here what we are considering, we are displacing the object and the object comes to its equilibrium position because of the restoring force. And we are not considering about the resistive forces that are acting on the system. That is what we have seen in simple harmonic oscillator. And then we have also derived the expression. So taking simply F is equal to minus Kx. F is ma according to Newton's second law of motion is equal to minus Kx, and A can be written as d square x by dt square because it is the rate of change of velocity is equal to minus Kx, or we can bring K onto the other side and divide throughout with m. We get d square x by dt square plus K by m into x is equal to 0. And this constant K by m can be written as omega square. K is a constant, spring constant, mass is also constant. So we are writing it, and that is equal to the square of the angular frequency. So we have this expression d square x by dt square plus omega square x is equal to 0. And nowhere, this is an idealistic case where we are not considering the damping forces or the resistive forces that are acting on the system. Then we have seen the damped harmonic oscillator. So in practical cases, in all cases, Always, whenever we consider a system, there is a resistive force. Even if you suspend a simple pendulum freely in air, the air exerts some resistive force on the motion or the oscillations of the simple pendulum. So we need to take into account the damping forces that are acting on the system. So what we have seen is the damping force is proportional to the velocity with which the mass moves. And this force, the damping force Fd, is given by minus gamma v. We are writing the damping force is proportional to the velocity and it is always acting in a direction opposite and the damping constant is gamma. So we have written Fd is equal to minus gamma v and v is nothing but dx by dt, rate of change of displacement. So we write it as dx by dt. Now, we also have the restoring force that is acting on the object. So, if we write the net force is the resistive force which acts in the opposite direction and also the damping force that acts in the direction opposite. So, what is the net force acting on the system is given by F is equal to minus kx minus gamma v. Now again, we are going to substitute for F, MA is equal to minus Kx and minus gamma V. So if you write MA is equal to minus Kx, which is the restoring force, and minus gamma V, which is the damping force, we have acceleration given by dx square by dt square. And we bring minus gamma V onto the other side, we have gamma. For V, we write dx by dt plus kx. We are bringing these two terms, kx and gamma v, onto the left hand side. So it becomes 0. Now dividing throughout with m, we get d square x by dt square plus gamma by m into dx by dt plus k by m into x. Means we are dividing throughout with m. Now we are going to substitute because gamma and m both are constants. Instead of gamma by m, we can put 2b. So d square x by dt square plus 2b into dx by dt plus k by m is omega square x is equal to 0. So this is a second order differential equation which takes into account the damping forces also. So this describes the motion of the block under the influence of damping forces and that is proportional to the velocity. Now we are coming to forced oscillations. Before understanding forced oscillations, let us see what are free oscillations. What are free oscillations? Let us take the example of a simple pendulum. You take a small bob, attach it to a string. This is an inextensible string. This is a rigid support. So when you just take it, this is the equilibrium position. You disturb it from the equilibrium position and leave it. So the pendulum keeps on oscillating about the mean position or the equilibrium position. So when a body is disturbed from its equilibrium position and is allowed to oscillate freely without any external force, then the body oscillates with its own natural frequency. So whenever we are disturbing it from the mean position and just leaving it and allowing it to oscillate freely, means the body will oscillate with its own natural frequency. And such oscillations, we call them as free oscillations. We are just disturbing it and leaving it. We are not applying any force. Without the application of force, the oscillations keep on continuing. And such oscillations, we call them as free oscillations. Now, all free oscillations eventually die out due to the ever-present damping forces. So, we have seen in the last slide, there are some forces that are acting in a direction opposite to the velocity. So, these damping forces will try to bring the object to rest. So, the oscillations will gradually come down and the amplitude decreases and they die out. And if we have to maintain these oscillations, we need an external agency. Only an external agency can maintain these oscillations. And when you are applying an external agency, then we will call them as forced or driven oscillations. Means we are putting some external force to sustain these oscillations. Then we call it as forced or driven oscillations. So the motion of the system under this external agency is known as forced simple harmonic motion. So whenever we talk about forced simple harmonic oscillator or forced simple harmonic motion, means the system is performing under an external agency. Means we are providing an external force. So this external force itself is periodic with a frequency P and is known as the drive frequency. Periodic again means it repeats after regular intervals of time. You apply a force to sustain the oscillations. So eventually they start dying out. Again you apply a force. So in periodic intervals we are applying a force with a frequency P. So we will call it as the drive frequency. Means the frequency that drives the oscillations or sustains the oscillations. Now one important point to remember here is the system oscillates with the driven frequency and not the natural frequency. In case of free oscillations, we have seen that the system will vibrate with its natural frequency. They are free oscillations. But here, it is not vibrating with its natural frequency. It will oscillate with the driven frequency, means the frequency, the periodic frequency which we are applying. Now, if it oscillates with the natural frequency, what is happening? The motion will die out. So let us understand this concept with the help of an example. The simple example is a child that swinging on a swing. Child, when he or she sits on the swing and starts swinging, initially what is done is he displaces itself from the main position and then starts swinging. But eventually what happens? The oscillations die out. The swing comes to rest. But then what happens? He will apply some force. Either with his feet, he uses his feet to move the swing, or if it's a small child, somebody will push them from the back. So they will give them a forward push, means apply a force. So to sustain or maintain the oscillations. Otherwise, the child cannot swing continuously. Eventually, if it is with the natural frequency, they will die out and the swing will come to rest. Now let us understand the difference, or we'll try to differentiate between free vibrations and forced vibrations. So in free vibrations, if the body is displaced from its equilibrium position and released, the restoring force acting on the body may set it into vibrations, and such vibrations are called free vibrations. We are just displacing the body and leaving. The restoring force tries to bring it back to the equilibrium position and tries to keep it oscillating. And such oscillations are called free oscillations or free vibrations. Now, in forced, what we see, the vibrations are under the action of an external periodic force, in which the body vibrates with the frequency equal to the frequency of the external periodic force. Now, they are not oscillating with the natural frequency, but the vibrations are dependent upon the external frequency we are applying. And such vibrations we are calling as forced vibrations. And the frequency of vibration is called the natural frequency here. In free vibrations, it is natural frequency and it depends upon the mass, dimensions and elastic properties of the modes of vibration of the vibrating body. But in forced oscillations, the frequency is equal to that of the external periodic force, whatever periodic force we are applying. So the system will oscillate with the same frequency. So the examples here we are taking is a simple pendulum for free oscillations and the vibrations of pendulum in a clock. In a clock, we are trying to sustain the oscillations, so they are forced vibrations or forced oscillations. Now let us go to derive the expression for a forced harmonic oscillator. Expression for a forced harmonic oscillator. So we will consider an external force Ft. F of t means, because we said it is periodic, we are considering this as the external force whose amplitude is F naught and it varies periodically with time. So we are taking a frequency period which is periodic, and this force is applied to a damped oscillator. Means we are already considering the damping forces that are acting on the system. Now on this system we are considering an external force. So how do we represent this force? F of t is given by F naught sine pt. Why sine pt? P is the frequency of the external periodic force. So we have to consider the periodic. We are taking a sine function because we are telling that it is a periodic force. So Ft is equal to F naught sine pt. Now what are the forces that are acting on the oscillator? One is the restoring force. The first one is the restoring force. And the second one is the damping force. And the third one is the time-dependent driving force. There are three forces that are acting on the system now. So now let us write the expression for the net force or the resultant force that is acting on the system. So F is equal to minus Kx, which is the restoring force which acts in a direction opposite to the displacement, minus gamma v. This is the damping force which acts in a direction opposite to the velocity, and F naught sine pt acts in the same direction as the force. So what we are writing here is F is equal to minus Kx minus gamma v plus F naught sine pt. So Kx, or I'll write minus Kx, represents the restoring force. And minus gamma v represents the damping force. And F naught sine pt is the periodic force that we are applying. This is the periodic force. So we have taken all three into consideration and we have written the equation. So now let us write the equation. So once we have F is equal to minus Kx minus gamma v plus F naught sine pt. So we'll be substituting in this now. So we know F is equal to ma according to Newton's second law of motion, and we write it as m into d square x by dt square. So for F, what we are substituting? M into d square x by dt square, and Kx. First we are writing the gamma term. So this is gamma into V. V is nothing but dx by dt plus Kx is equal to F naught sine pt. Means here I have taken the terms onto the other side, plus gamma V plus Kx. So minus gamma V and minus Kx I am taking onto the left hand side. We get F plus gamma V plus Kx is equal to F naught sine pt. And here I am substituting for F m into d square x by dt square plus gamma. For V we are substituting dx by dt plus Kx is equal to F naught sine pt. So that is what we are seeing in equation 3. Now equation 3 is the equation of an oscillator of mass m which is moving with a periodic frequency p. Obviously what we see here is the oscillator first oscillates with its natural frequency, and when we apply the external periodic force, the natural frequency will die out and the body will start moving with the driven frequency, that is the p. Now let us write the equation for this. We have taken m into d square x by dt square plus gamma into dx by dt plus kx is equal to f naught sine pt. We will divide throughout with m because we are going to bring in the second order differential equation. So divide throughout with m. So we get d square x by dt square plus gamma by m into dx by dt plus k by m into x is equal to f naught by m into sine pt. And we know that gamma by m we are replacing with 2b. So this will be 2b dx by dt. We have d square x by dt square plus k by m is omega square. And for f naught by m we will write f. So what we have done here is for gamma by m we are substituting 2b. For k by m we are substituting omega square. And for f naught by m we are substituting f. So that is what we have written here, the substituting terms. So what is the final expression we are getting is this. The same. Now, the solution of this differential equation will give us the displacement. So, what is the displacement given by xt is equal to a sine pt minus theta. This is the solution of the given differential equation which gives us the displacement. And t is the time from the moment we apply the external periodic force. And capital A is the amplitude. And theta is the angle by which the displacement lags behind the applied force. So when we are applying a force, what is the angle by which the displacement lags behind the force? And P here is the frequency of the applied force. So all the terms are clear. When we are talking about the displacement given by xt is equal to a sine pt minus theta. X is the displacement, a is the amplitude. Amplitude is what? It is the maximum displacement from the equilibrium position. P represents the frequency, t is the time, and theta is the angular displacement or the angle by which the displacement lags behind the applied force. So once we have x is equal to a sine pt minus theta, we can calculate the velocity. What is velocity? Velocity v is equal to dx by dt. So taking the derivative of x, so d by dt of a sine pt minus theta. So we are taking the derivative with respect to time. So a is a constant. So for sine we get cos pt minus theta, and for pt we get p. So the velocity will be given by ap cos pt minus theta. So this is the velocity, which is what we are writing here. dx by dt is nothing but velocity. ap cos pt minus theta, simply by differentiating, because we have the displacement, so we can find the velocity. We also can find the acceleration. What is acceleration? A is equal to dv by dt. So we are going to do d by dt of v. What is v? ap cos pt minus theta. This is v. So again we will put the constants outside. ap, derivative of cos, d by dt of cos pt minus theta is minus sine pt minus theta, and for pt we get p. So we can rearrange the terms and we'll write the minus first, and ap into p will be ap square sine pt minus theta. So what we are getting for acceleration is minus ap square into sine pt minus theta. So when we substitute these equations in 4, what we get? D square x by dt square plus 2b dx by dt plus omega square x is equal to f sine pt. And when we solve, we are substituting these two in this equation. We have got dA square x by dt square. We have got dx by dt. Substitute them here. we get amplitude of the vibration and also the phase of the vibration. To get the amplitude as well as phase, we substitute these two expressions here and we'll directly write the solution. So the amplitude of vibration is given by A is equal to F upon under root omega square minus P square whole square plus 4B square P square. No, the derivation is not there in your syllabus. If you want to know the derivation, you can refer to Engineering Physics by Gaur and Gupta, where the detailed expression is given. Otherwise, we'll be using this expression for amplitude by solving, and then we will discuss the conditions. So let us now see what are these terms. Omega is the natural angular frequency. P is the frequency of the applied force. So what we have here, omega, natural frequency. P is the frequency of the applied force. B is a constant we have taken, where B is equal to gamma by 2m, which is depending upon the damping coefficient. Gamma we have taken as the damping constant. So B corresponds to the damping coefficient. And what is F here? F is F naught by m, which corresponds to the external force applied. So what is it that the amplitude depends on? It depends upon the natural frequency and the external periodic frequency, the damping coefficient, and also the external force that is applied. And then the phase difference. What is the phase difference? That is theta is equal to tan inverse 2bp by omega square minus p square. So all the terms we have seen. What is omega? What is p? What is b? We have seen. So we can find the amplitude and phase for different conditions. Now, depending upon the values of P and omega, that is the driving frequency and the natural frequency, we have three cases. What happens if the driving frequency is low? Means the frequency, the external periodic frequency which we are applying is less than the natural frequency. That is, the condition here is P less than omega. The external periodic frequency is less than the natural frequency. So we are going to apply this condition in the formula for amplitude. What is A? So whatever I have put in blue are the reference expressions, because we are going to refer this expression to get the necessary conditions. So A is equal to F upon under root omega square minus P square plus 4B square P square. So P is very much less than omega. So this term can simply be neglected. We can neglect. And here also this term also can be neglected. So what we have here is F under root A is equal to F by under root omega square whole square. So square and square root get cancelled. So we have A is equal to F upon omega. So we are writing as B tends to 0, the amplitude is given by A is equal to F by omega square. Now the second thing is the amplitude of vibration depends upon the force F naught and the force constant K. So it is depending on the force F naught also and the force constant K also. Now what is the phase? How do we calculate the phase? So we have the expression for theta. Theta is tan inverse 2bp by omega square minus p square. So we have taken that b tends to 0. So the whole thing becomes 0. So what we have here is tan inverse 0 is 0. So theta is equal to 0 means there is no phase lag. The displacement and the applied force are in phase. So theta is equal to 0 implies that they are in phase and there is no phase lag between the applied force and the displacement. Now let us see the second case where the driving frequency P is equal to the natural frequency. We'll have a special condition. This is called as resonance. We'll try to understand resonance also with the help of this expression. So let us now put this condition P is equal to omega in the expression. So what is our expression? A is equal to F upon under root omega square minus P square plus 4b square p square. So when omega is equal to p, see this whole term, omega square minus p square will give us 0. This gets cancelled. So what we have here is a is equal to f upon root 4b square p square. So I can as well write it as f upon under root 2bp whole square. So the square and square root will get cancelled. So we get a is equal to f upon 2b. So this is the expression we have written. So the amplitude now depends upon the damping coefficient, the external periodic frequency p and the applied force. Now what about theta? Theta is equal to tan inverse 2bp by omega square minus p square. So when these two are equal, the denominator is 0. So something upon 0, what you have is tan inverse infinity. 1 by 0 or some constant upon 0, we have infinity. So what we are seeing here, theta is equal to tan inverse infinity. So when do we get infinity? For pi by 2. So what we are concluding from here is amplitude depends upon the damping coefficient R, and for small damping amplitude is very large. So if the value of B is small, the amplitude will be large. So the reverse, the converse is also true. If B is large, amplitude is small. And then what is the phase difference? They are differing in phase. The displacement and the applied force differ in phase by pi by 2. Now, this condition P is equal to omega means the applied frequency, when it becomes equal to the natural frequency, we have a special condition called resonance. So what is resonance? First, we'll try to understand the phenomenon of resonance. So the increase in amplitude when driving force is close to the natural frequency. So when the driving force matches with the natural frequency of the oscillator, then the system will vibrate with a very large amplitude. So to understand this, we will take one example. What we'll do here is we'll consider 3 pendulums of nearly equal but not equal lengths. Okay, we'll consider 3 pendulums that are suspended from a rigid support. So you can see here 3 pendulums. They are all suspended from a rigid support. They are not exactly equal in length, but they appear to be equal, slightly equal in length. So now the first pendulum is set into oscillation. This is the first one. Set into oscillation. We are just displacing it from the mean position. And then what happens after some time 2 also starts vibrating. Now, after some time what happens if the frequency or the natural frequency of 2 matches with the external frequency which we are applying, this will start vibrating with a larger amplitude. That is what we are going to see here. You see here initially it was vibrating with a very small amplitude, but as the oscillations move on, it will start, whenever these two match, the external periodic force matches with the natural frequency, it will start oscillating with a greater amplitude. That is the phenomenon of resonance. So let us understand what we are seeing here. We swing the first pendulum, which is greater in length. It will oscillate with its natural frequency because we are not applying any external force. We are just displacing it from the mean position and leaving. So the first pendulum will oscillate with its natural frequency. And the energy of this pendulum is transferred through the rigid support to the second pendulum. Means we are applying some force on the second pendulum. So the second pendulum starts oscillating with the natural frequency first. And at one particular point, what happens? The frequency with which the second pendulum vibrates becomes equal to the first one. Means the natural frequency of the second pendulum is changing. It will die out gradually and it will start vibrating with the external periodic frequency. That is the frequency of the first one. So therefore, what happens now? The second pendulum starts with the frequency of the first one, which is the driven frequency. And when this happens, the amplitude of oscillations is the maximum. And this is called resonance. So let us see some examples of resonance. So like damping, resonance also can be wanted and sometimes unwanted. In some cases, we have seen we need damping and some cases we don't need damping. The same way, in some cases we need resonance and some cases we need to avoid resonance. So what are the examples? Musical instruments and TV radio receivers depend on resonance. So whenever the signals are transmitted from a transmitter, so there will be a receiver in the TV or the radio. So whatever frequencies that are transmitted, if that matches with the tuning of the radio, then it will receive it. So that works on the principle of resonance. Now, the second example is bridges may collapse due to resonance. So it may seem to be impractical, but if you see, you must have studied that soldiers are not allowed to march on the bridge. What is the reason behind it is, when a bridge is constructed, there is a particular frequency with which it is permitted to oscillate. No? So there will be some elasticity for that, so that the bridge can oscillate. Wherever you see a vehicle moving on a bridge, so you see some vibrations in the bridge. Now, you know how soldiers march. So they march with a very particular frequency, and the frequency of all the soldiers will match exactly. So rhythmic it will be. And if the marching frequency of the soldiers matches with the frequency of the bridge, and if they match together, there is resonance. So in resonance, what happens? The amplitude increases. The bridge may start vibrating with larger amplitude more than the permitted value. Then what happens? The bridge may collapse. So that is why care has to be taken to avoid resonance in such cases, so that the bridges will not collapse. And also during earthquakes, buildings collapse. Sometimes the earthquake may be not very high on a Richter scale, but still there is lot of damage, lot of destruction caused, and many buildings collapse. This is also because of resonance. So when the frequency matches with the frequency of the building, and it will vibrate with a larger frequency, so it may collapse. Now coming to the third case where P is much greater than the natural frequency. So the driving frequency is more than the natural frequency. So let us put this condition in the formula for amplitude. A is equal to F upon under root omega square minus P square whole square plus 4B square P square. So what we are going to do here is, because P is bigger, we can simply eliminate this term. What we get here is F by P square under root P square. So A is equal to F upon under root P square whole square. So we have A is equal to F upon P square. And here also what we have, P is greater, so we are neglecting, so we'll have a negative term. So minus 0. So tan inverse of minus 0 is pi. So what we see here, the amplitude of vibration depends upon the frequency of the applied force. Now it is no more dependent on the damping coefficient. It simply depends upon the frequency of the driving force. And at high applied frequencies, the amplitude will decrease. What about the phase difference? They differ in phase by pi, that is 180. So the phase difference is pi. Now, what are the conclusions that we can draw from these three cases which we have seen? When the driving frequency is less, the amplitude increases with increase in P. This is the first conclusion. And when omega is equal to P, means the driving frequency is equal to the natural frequency. It reaches the infinity. The amplitude is infinite. We said the amplitude becomes maximum So we are talking at as infinity. Amplitude is maximum here. When we have seen that omega is equal to P, which gives rise to resonance, and the resultant of which is amplitude maximum. And the third point is smaller the damping, sharper the resonance. So whenever the damping is small, the resonance is sharp. So larger the damping, flatter the resonance. So here you can understand this with the help of this figure. When the damping is small, you will see a sharp peak here, like this. And when there is heavy damping, the peak is flat, like this. So that is what we try to understand. And with further increase in the driving frequency, the magnitude of amplitude increases. So the last case, what we have seen, as we are keeping on increasing the driving frequency, the magnitude of amplitude goes on increase. Now coming to the quality factor. So the width of the resonant peak can be characterized by the quality factor, and the quality factor Q depends upon the mass. It also depends upon the natural frequency and the damping coefficient. So M here is the mass. Omega naught is the initial angular frequency. And B corresponds to damping coefficient, because 2B is equal to gamma bar M. So B corresponds to the damping coefficient. Now, why do we need this quality factor? It is always necessary to describe the quality of an oscillator. How good it is, how it is oscillating, whether oscillations are sustained or not sustained, or how is the damping. All that is described by the quality factor. Smaller the degree of damping, higher the quality of the oscillator. So what we understand, here you see they are inversely proportional. So if the value of B increases, Q decreases. So if the damping increases, the quality factor decreases. The quality of the oscillator decreases. And the width of the resonant peak can be characterized by Q factor. So you can also define the width of the peak. It can also be calculated with the help of Q factor. And this Q factor is dimensionless, and it can be readily applied to any oscillator. You can apply this formula for any type of oscillator. Now, with the help of this, we'll try to understand what a forced electrical oscillator is. So whenever we are dealing with electrical circuits, so an electrical circuit which involves inductance, capacitance and resistance. So we are considering an LCR circuit, an electrical circuit which is having all the three. And here it is driven by a voltage E naught sine omega t. So periodic we said. So whenever we are applying a periodic frequency, so we are denoting it by E naught sine omega t. So the driving voltage here is analogous to the force that is applied in a mechanical oscillator. So how do we write the expression now? For an LCR circuit, we have seen in a closed loop according to Kirchhoff's law, VL plus VR plus VC should be equal to E naught sine omega t. Okay, so VL is the voltage across the inductance, R voltage across resistance, C the voltage across capacitance. So how do we write VL? VL is nothing but L into di by dt. VR is given by IR and C is given by Q by C. So here we are going to substitute for I is equal to dQ by dt. What is I? The current. Current is nothing but the rate of flow of charge. So I is equal to dQ by dt. So when we substitute for I here, we get d square Q by dt square plus R by L, because we are going to divide throughout with L. So let us take this equation. This equation, I'll consider this is equation 1, this is equation 2. So in equation 2, we are going to substitute for I. So what we get here is L into d square q by dt square plus R into dq by dt plus q by c is equal to E naught sine omega. Now to write the differential equation, we are going to divide throughout with L. So when we divide throughout with L, what we get? D square q by dt square plus R by L into dq by dt plus q by CL is equal to E naught sine omega t upon L, of course. So we are getting this expression. Now we will apply the same to a mechanical oscillator. So how do we relate electrical oscillator to mechanical oscillator? So whatever the displacement x we are talking about, here it is analogous to charge. And the mass m is analogous to the inductance L. And the constant, spring constant K, is analogous to 1 by C. And where we have taken V is equal to dx by dt, here we are taking I is equal to dq by dt. So once you get this analogy, you will be able to clearly understand the electrical oscillator. And there we have taken the angular frequency omega square is equal to k by m. And here omega square will be given by 1 upon LC. And F naught sine pt is the driving frequency there. Here it is E naught sine omega t. Now let us see what is mechanical impedance. So it is a measure of how much a system resists the motion when subjected to harmonic force. So we are talking about a forced harmonic oscillator, means we are taking a system where there are damping forces that are already acting on it, and in order to sustain the oscillations, we are applying a force on it. So now mechanical impedance tells us, or it gives us the measure of how much the system resists the motion when subjected to harmonic force. And it relates forces with velocities that are acting on the mechanical system. So how do we calculate? It is the ratio of the force applied at a point to the resulting velocity at that point. So at any given point, if you have to calculate the mechanical impedance, it is the ratio of the force applied to the resultant velocity. And this mechanical impedance is also inverse of mobility, mechanical mobility. So impedance is the resistance, mobility is which keeps in motion. So it is inversely proportional. And the mechanical impedance is a function of frequency omega of the applied force and can vary greatly over frequency. Means if the frequency varies, the mechanical impedance also varies. Now let us see electrical impedance. What is electrical impedance? Impedance here is generally denoted by Z. And it is an expression which talks about the opposition that an electronic component or a circuit offers to the alternating current or the direct current. So whenever we talk about impedance, it is always talking about the resistance or the opposition to the flow of current in an electric circuit or in an electric component. So in case of this, we have two independent scalars. No? Resistance, which is denoted by R, and reactance, that is denoted by S. So we'll see what is resistance and what is reactance. So resistance is a measure of the extent which a substance opposes the movement of electrons among its atoms. So resistance, whenever we talk, it is the resistance that is offered to the movement of electrons in a circuit. Then reactance is an expression of the extent to which an electronic component or a circuit or a system stores and releases the energy. So reactance talks about how the energy is stored or released when the current flows through the circuit. Means for each cycle, how the energy is stored and released. That can be measured with the help of reactance. Now, what are the formula? In the case of impedance of an electrical oscillator, Z is equal to under root R square plus 1 by omega C minus 1 by omega L whole square. You need not derive the expressions. You will be using these expressions to calculate the impedance. R is the resistance, omega is the angular frequency, C the capacitance, and L the inductance. So 1 by omega C reactance due to the capacitance and omega L due to inductance. Now, what is the impedance in case of a mechanical oscillator? So, Z is equal to under root B square plus K by omega minus omega M whole square. So, K by omega is the reactance here due to the stiffness in the spring and omega M due to the mass. So, we have a mass M, we have a spring constant. So, what is the reactance due to the stiffness in the spring and due to the mass? That helps us to calculate the impedance in a mechanical oscillator. Now coming to the phase difference, that is a phase difference between the EMF and the current. In an electrical oscillator, it is given by tan phi is equal to 1 by omega C minus omega L upon R. And if it is a mechanical oscillator, it is K by omega minus omega M by B. So we have seen the analogy. 1 by omega C is analogous to K by omega and omega L analogous to omega M. And here B, the damping coefficient, is analogous to the resistance. So we have these formula to calculate the phase difference between the EMF and the current. Now coming to the resonant frequency. Electrical resonance takes place when the impedance is minimum. So when is the impedance minimum? When omega L is equal to 1 by omega C. So omega L is equal to 1 by omega C means I can also rewrite it as omega square is equal to 1 upon LC, or omega is equal to under root LC. We know omega is equal to 2 pi F. Angular frequency is given by 2 pi F is equal to 1 upon root LC. I may write it as N also. We can represent frequency by N sometimes or by F. So if you are writing it by N, 2 pi N. So N will be equal to 1 upon 2 pi under root LC. So you can calculate the corresponding resonant frequency. And for a mechanical oscillator, how do we get N is equal to 1 by 2 pi under root K by M. Similar way, if you derive, you get N is equal to 1 by 2 pi under root K by M. So at resonant frequency, what happens? The amplitude of oscillation becomes maximum. So whenever these conditions are satisfied, the amplitude is always maximum. So let us conclude the session here. For more details, you can refer to Engineering Physics by Harbola, Vijay Krishna and Madhu Mohan by Cengage Publications. And you can also refer to Gaur and Gupta Engineering Physics. Thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.